Okay, just revisiting Kepler's third law here. I'm going to just kind of show you how this is actually accomplished. I show you in my notes, but just to illustrate it a little further here. Um, we know here that something, traveling or orbiting a planet is going to have a certain centripetal acceleration. That centripetal acceleration will be equal to v squared over r. This will also be equal to the acceleration due to gravity, which is equal to g m of the center body divided by r squared. So both these are equivalent here. And I'm going to try to relate these here now. And I did this last time for showing the speed of a satellite. But I'm going to take it a step further and just really dive into what is v. And recall that v is equal to 2 pi r all over the period. So I'm going to plug this in for v. And what I'm going to get here is instead I'm going to get, if I have 2 pi r over t squared all over r, that's going to equal g m cb over r squared. I'm going to square this top term. And what I'm going to get here is I'm going to get 4, 2 squared, pi squared times r squared, all divided by r, which equals g mcb over r squared. Moving some things around, oh, I forgot about the t squared, pardon me. The t here would come on the bottom, so if I do that, you're going to get here t squared. Okay, so this is 2 pi r over t squared. Let's try to rearrange some things here. I can get rid of, let's see here, I can get rid of this squared and that one. This r can come to the top, and I'm going to move the 4 pi squared to the bottom. In which case here, I'm going to get, so let's see here, this is going to become, well, I'll write this like this and say 4 pi squared r cubed over t squared is equal to g mcb. The last thing I'm going to do is divide by 4 pi squared, and you're going to get here r cubed over t squared is equal to g mcb over 4 pi squared. Now I think, I may show this in my notes as t squared over r cubed is equal to 4 pi squared over g mcb. It's the same thing, it's just flipped. The important thing here is, what does this mean? Well, Kepler's third law essentially says that any planet, okay, going around a center body only depends on actually the mass of the center body. It doesn't depend on anything else. In other words, the period, okay, and the radius of that planet will have some proportion that will equal this constant. Okay, so in other words, let me illustrate that a little further. I'm going to just move this and kind of show it in the same way. I'm going to write this like this now and say t squared over r cubed, just flip it, is equal to this. What this means essentially is that if I have, let's say, the sun, okay, and there are planets going around their sun, maybe one here, it could be Mercury, maybe Earth is over here. They're getting further and further away. But it turns out that this proportion of how long it takes to go one complete cycle, the period, divided by how far it is away from the center, the radius, if I square it and cube it, I end up getting a constant. This is what Kepler noticed. It's always the same number. The Earth has the same, Jupiter has the same. It's all the same as long as they're going around the same center body. In other words, any satellite going around the Earth, including the Moon, would all also obey this. Of course, this would be a different result because we're talking about the Earth as opposed to the Sun. But for each of those satellites, they would be the same. Why is this important? Well, if you already know the constant, you can start figuring out other things. In other words, you could figure out the mass of any center body knowing a satellite's period and its radius. You can also start doing this. If you know this is a constant and saying, well, let's suppose we knew the Earth's period, and you know what, I can say here that the Earth's period is going to be 1 year. There's the Earth's period, 1 year. How far is the Earth away from the Sun? I'm going to say 1. In other words, I can make up units because I don't need to put in actual numbers unless I'm figuring out the mass. But if I want to compare two satellites, I can say my own unit, which is going to be 1 year and 1 distance away from the Sun. Okay, 1 distance away from the Sun. So I'll call it Earth-Sun distance. Okay, 1 Earth-Sun. I'm going to cube that. If I want to compare this to, let's say, another satellite going around the Sun, I'll just make one up. And suppose another satellite takes, 3 Earth years. Okay, what I can get from this is I can get how far is that satellite away from the sun. I'll call it RSS for satellite of the sun. I know all these numbers, and what's nice about this is I can work with simple numbers, okay, to get a complicated thing. And now I can figure out how far that fictitious satellite is away from the sun by just rearranging this in terms of Earth years. Okay, not a scientific unit, but we can just call it Earth years. And you can do the same thing for radius and how far things are away. You can compare them. This was Kepler's third law. Again, you can branch this out even further to get in terms of how to figure out the masses.